Summer of 1940, Royal Air Force, Hornchurch Airfield, Essex. On the concrete apron, two identical Supermarine Spitfires stand side by side, engines silent but waiting. Same Merlin engine, same 8 guns, same pilot strapped into the cockpit. Only one difference will decide history. Squadron leader Desmond Cook throttles up the first aircraft. The Spitfire roars forward, takeoff run 320 yards, climbing to 20,000 feet in 11 minutes and 8 seconds. No one knows yet these numbers are about to be rewritten forever. At the service ceiling where the air grows thin and engines gasp, the first Spitfire stalled at 32,000 feet. 20 minutes later, squadron leader Desmond Cook climbs into the second Spitfire, identical airframe, identical engine, different propeller. Takeoff run 225 yards, climb to 20,000 feet, 7 minutes and 42 seconds. Service ceiling 39,000 feet. Same plane, same engine, same war, but those 3 spinning blades just rewrote the balance of history. The difference between victory and defeat in the Battle of Britain came down to 3 spinning aluminum blades, the kind of invention aviation experts across America had once dismissed as impossibly complex. Frank Caldwell's impossible propeller design, the one that would make U.S. bombers fly 100 miles per hour faster, had just revealed its power over the English countryside. But the story of one stubborn engineer who let numbers and logic defeat an entire industry's assumptions begins 8 years earlier in a factory where everyone said his idea would never work. On a gray February morning of 1932, Frank Walker Caldwell stood inside the oil-stained test facility of Hamilton Standard Propeller Corporation in East Hartford, Connecticut. At 43 years old, the MIT-trained mechanical engineer had the measured calm of a man who trusted numbers more than opinions. Wire-rimmed glasses rested precisely on his nose, and his clipboard never left his calloused hands. The portrait of a craftsman scientist, surrounded by steel, oil, and equations, quietly believing that data could one day rewrite the history of flight. Behind him, mounted on a test stand that shook with mechanical fury, spun a gleaming metal propeller unlike anything aviation had ever seen. 3 aluminum blades changed their pitch while spinning at 2,400 revolutions per minute, roaring like a living creature born of steel and motion. Amid the haze of oil and smoke, Frank Caldwell stood still, watching the impossible take shape before his eyes. And then, 3 days earlier, a phone call from Boeing Field in Seattle had arrived, a call that would change everything from Caldwell's fate to the destiny of flight itself. The Boeing Model 247, America's revolutionary new airliner, sat stranded at Denver Municipal Airport like a thoroughbred, limping on broken legs. At an altitude of 5,280 feet, the twin-engine marvel that was meant to carry passengers from coast to coast in record time now struggled to climb over the Rocky Mountains. 2 wooden propeller blades fixed at a single pitch angle, optimized for one flight condition, had rendered the aircraft nearly useless everywhere else. In that moment, America's dream of flight was chained by the very technology that was supposed to set it free. That morning, Pan American Airways President Juan Trippe delivered a cold ultimatum to Boeing: fix it, or we're buying Douglas. The stakes had never been higher. United Airlines had 25 Model 247s on order, and TWA wanted 30 more. But every deal, every dream, every ounce of pride in American aviation meant nothing if the world's most advanced airliner couldn't climb over a single mountain range. Frank Caldwell had heard this tune before, the tune of doubt, of fear, of history about to repeat itself. Across America's aviation community, the old belief flowed like gospel from hangar to boardroom. They said variable pitch propellers are a solution looking for a problem. Too heavy for the gain, too complex for reliable operation. Too many precision-machined moving parts working in a hostile environment where oil froze at high altitude and vibration tore apart delicate mechanisms. In that world, skepticism was law and innovation was sin until one man dared to defy the system. The Army Air Corps Engineering Division had officially classified Caldwell's hydraulic design as mechanically unsound, a verdict cold as steel, written in black ink, yet strong enough to bury a revolution before it took flight. And worse still, even Charles Lindbergh, aviation's most celebrated voice, had doubted the concept. During a private meeting at Wright Field in the autumn of the previous year, the man who had once crossed the Atlantic alone asked quietly, "What happens if it fails at 30,000 feet?" Caldwell said nothing. He just stared at his numbers, where data spoke louder than doubt. But Caldwell carried the quiet confidence of an engineer who had been proven right before. From 1917 to 1928, as the government's chief propeller engineer, he had watched aviation experts resist metal propellers because wood was lighter and oppose ground-adjustable props for being too complex and unnecessary. Each time his data had shattered their assumptions, each time the industry had followed where his numbers led. But this time felt different. Ahead lay not just a technical debate, but a battle between logic and belief, between fear and progress. This time, it wasn't just an experiment, it was survival. Careers and companies hung in the balance. Hamilton Standard had bet everything on Caldwell's revolutionary idea: 800 jobs in East Hartford, plus manufacturing contracts stretching from Connecticut to California. The company that once built the propellers for Lindbergh's Spirit of St. Louis now stood on the edge between triumph and collapse, between flight and failure. A single error, a single miscalculation could bring the dream crashing down. Hamilton Standard, the company that built the propellers for the Spirit of St. Louis, might not survive if Caldwell's calculations were wrong. His entire reputation, forged over 25 years of propeller development, now rested on 3 spinning blades and a hydraulic governor system that used engine oil pressure to automatically adjust blade angle with every change. In flight conditions, the design was elegant in its simplicity, a machine so refined it looked effortless. As light shimmered across the metal, Caldwell watched the gauges flicker, knowing that one small error could destroy everything he had built. During takeoff and climb, when maximum power was needed, the propeller automatically shifted to fine pitch like a car's low gear, allowing the engine to spin faster and produce greater thrust. At cruising altitude, the system shifted to coarse pitch, giving maximum speed and fuel efficiency. If an engine failed, the propeller could feather its blades parallel to the airflow, eliminating drag that might otherwise pull the aircraft into a fatal spiral. The numbers spoke with mathematical certainty, a mechanism so elegant it redefined the boundaries of flight itself. At the wind tunnel tests at MIT, Caldwell had proven that constant-speed propellers could increase climb rate by 40%, extend service ceiling by 7,000 feet, and improve fuel efficiency by 15% across all flight regimes. But numbers meant nothing if the aviation industry refused to believe them. The breakthrough came on February 15, 1933, when United Airlines President Pat Patterson gave Hamilton Standard one final chance. One test flight with your impossible propeller installed on a Boeing Model 247. That day, on a single test flight, the future of American aviation took off. Test pilot Eddie Allen, a former Navy aviator with ice water in his veins, was chosen to put Caldwell's theory to the ultimate test. The flight took place over the same Rocky Mountain range that had grounded identical aircraft 2 weeks earlier. Allen climbed steadily past 6,000 feet, then 8,000, then 10,000 feet, crossing the Continental Divide as if it were nothing more than a speed bump on a quiet country road. In that moment, technology's limits shattered, and Caldwell's numbers finally took flight. The constant speed propeller automatically adjusted to every change in altitude, maintaining optimal engine RPM while maximizing thrust. Where the fixed-pitch aircraft had struggled to reach 6,000 feet over Denver, the modified Model 247 climbed to a service ceiling of 20,700 feet, a leap that rewrote aviation performance. Its cruise speed was equally impressive, 15 miles per hour faster at every altitude, with 12% better fuel efficiency at normal cruise power settings. That evening, Patterson received the telegram with the results and knew at once that American aviation had entered a new era. Constant speed propeller exceeds all performance claims. Recommend immediate adoption for entire United fleet. The telegram was brief, yet it shook American aviation to its core. Caldwell's invention had triumphed. Hamilton Standard in East Hartford overflowed with new orders. But as machines celebrated progress, a darker reality was taking shape beyond the hangars. In Germany, the Nazi Party had seized power. In Japan, military leaders spoke openly of Pacific expansion. While Caldwell perfected the future of flight, the storm of war was already gathering over the horizon. War clouds were gathering over Europe and Asia, and the propeller technology once designed for passenger comfort was about to become America's secret weapon. The telephone rang in Frank Caldwell's office on a humid May morning in 1933. The caller introduced himself as Commander John Towers from the Navy Department's Bureau of Aeronautics. "We'd like to discuss fighters," he said, "fast fighters that could outclimb and outrun anything the Germans or Japanese were building, and bombers that could fly higher and faster than enemy interceptors could ever reach." At that moment, Caldwell realized the invention born for civilian skies was now destined for warfare. The age of aerial warfare was dawning, and Frank Caldwell held the key to unlock America's air superiority. On November 13, 1933, a telegram arrived at the Hamilton Standard headquarters carrying the words that would vindicate everything he had fought for. The National Aeronautic Association announced that the Hamilton Standard Propeller Corporation had won the Collier Trophy, aviation's highest honor, awarded for the development of a controllable pitch propeller, with special credit to Frank W. Caldwell. In that moment, the man once called a dreamer had proven his dream could fly. President Franklin Roosevelt personally congratulated Frank Caldwell at the White House in December. But even as photographers captured the moment he shook hands with the president, the aviation establishment remained stubbornly skeptical. At Wright Field in Dayton, Ohio, Army test pilots complained bitterly about the extra complexity that constant-speed propellers introduced into combat aircraft. While the world saw glory and applause, Caldwell saw only another challenge, proving that true simplicity lies in a system smart enough to think for itself. Major Benjamin Kelsey, chief of the Army Air Corps Fighter Projects Office, voiced the concern that echoed through hangars across America. What happens when that hydraulic system fails over Germany? When oil pressure drops and the propeller locks up, fixed pitch props don't break because there's nothing to break. The words hit like steel, striking steel, capturing every pilot's hidden fear, death from one's own invention. But Caldwell didn't argue or defend. His response was, as always, methodical, measured, and calm. To him, fear was simply another variable to test, calculate, and conquer. If military aviators demanded proof of reliability under combat conditions, Caldwell would give them data that left no room for doubt. Working 18-hour days inside Hamilton Standard's expanded test facility, he invented what became known as the whirl test. Propellers were mounted on fixed stands to measure thrust endurance, speed, and structural strength under conditions harsher than anything an aircraft would ever face in real combat. The technical breakthrough that made everything possible was elegant in its mechanical simplicity, proving that true genius doesn't need complexity, only precision. Simplicity, that was Caldwell's genius. His hydromatic propeller used engine oil pressure to drive a piston, changing the blade angle through a system of gears and counterweights. A centrifugal governor, no larger than a coffee can, maintained constant revolutions per minute, automatically adjusting blade pitch to match every flight condition. As the aircraft climbed and air density decreased, the propeller shifted to fine pitch, aviation's equivalent of low gear, maintaining engine revolutions and maximizing power. During cruise flight, it shifted to coarse pitch for maximum speed and fuel efficiency. A machine that could think in motion where mechanical grace replaced human control. When the aircraft dived too fast, the propeller automatically shifted to a coarser pitch, preventing the engine from overspeed damage. But the most revolutionary innovation was the feathering capability, the ability to align the propeller blades parallel to the airflow. If one engine failed completely, oil pressure from the remaining engines could rotate the dead propeller's blades to match the wind, eliminating the massive drag that would otherwise pull a multi-engine aircraft into an uncontrollable spiral. A small piece of engineering, yet it would save thousands of airmen through mechanics, logic, and faith in precision. For bomber crews flying deep into enemy territory, this single feature could mean the difference between limping home on the remaining engines or becoming another forgotten statistic. The performance improvements were no longer just numbers, they became undeniable combat capability. A P-51 Mustang fitted with Caldwell's constant-speed propeller, compared to the same aircraft with fixed-pitch blades, showed dramatic differences across every flight regime. from takeoff and climb to cruise, and return, proving that the right engineering doesn't just make you faster, it keeps you alive. Takeoff distance was reduced by 30%, allowing American fighters to scramble from shorter airfields closer to the front lines. Rate of climb increased by 40%, cutting precious minutes from the time required to reach intercept altitude. Service ceiling jumped by 7,000 feet, giving U.S. pilots complete altitude superiority over enemy aircraft. Numbers on paper, but in combat, they marked the thin line between survival and defeat, between the hunted and the hunter. Combat range extended by 200 miles, and fuel efficiency improved by 15% across all power settings. But numbers on a test report meant nothing if the propellers failed when pilots needed them most. Caldwell's obsession with reliability drove him to push every component beyond its design limits, testing each piece until nothing could break anymore. He didn't just want propellers to work, he wanted them to survive anything, just as men must survive the war itself. Propeller blades were tested under loads 50% higher than maximum combat stress. Hydraulic governors ran 500 continuous hours through brutal conditions, from 40 degrees below zero to 160 degrees Fahrenheit. Even the oil seals were contaminated with debris to simulate battle damage and maintenance neglect, proving the system could survive real war. In a world where a single flaw could cost lives, Caldwell faced risk not with fear, but with steel and data. As Hamilton Standard's order books filled with military contracts, the resistance from established aviation manufacturers grew louder and more determined. Curtiss Wright, the maker of fixed-pitch propellers for most Army Air Corps fighters, launched a lobbying campaign claiming that constant-speed propellers were an unnecessary complication that would cost American pilots their lives. Their chief engineer, Dr. George Meade, led the charge, a battle fought not with bullets but with ego, fear, and tradition. Through the noise and accusations, Frank Caldwell said nothing. He let the data speak for him. Dr. George Meade published a series of technical papers questioning whether hydraulic systems could operate reliably at combat altitudes, where temperatures dropped to 60 degrees below zero and oil viscosity increased dramatically. But Caldwell didn't argue with words, he answered with data. His cold weather tests at 35,000 feet proved the opposite. The hydromatic system not only remained stable, but actually performed better at high altitude because thicker oil provided stronger and more consistent pressure control. Vibration tests revealed that constant-speed propellers suffered fewer mechanical failures than fixed-pitch designs because the automatic pitch adjustment system eliminated the resonance frequencies that cracked propeller hubs and loosened mounting bolts. Caldwell realized that in engineering, strength means balance, and harmony between moving parts is what keeps machines alive. The breakthrough moment came during a demonstration at Selfridge Field in Michigan on March 21, 1934. Two identical P-26 fighters took off side by side, one equipped with the standard fixed-pitch propeller, the other with Caldwell's constant speed system. The difference in performance was so astonishing that the observing pilots initially believed the constant-speed aircraft carried a stronger engine tuned for maximum power at 10,000 feet. Up there in the blue sky, technology proved its worth not through words, but through speed, climb, and undeniable truth. Two identical P-26 pea shooters take off side by side, same engine, same weight, only the propeller differs. The first, with a fixed-pitch propeller, reaches 10,000 feet in 8 minutes and 30 seconds. The second, with a constant-speed propeller, climbs the same altitude in 5 minutes and 40 seconds. Maximum speed at 15,000 feet, 187 miles per hour, versus 203 miles per hour. Service ceiling 28,000 feet against 34,500 feet. The difference wasn't just numbers, it was a revolution in performance. Lieutenant Colonel Carl Spaatz, who would later command all American strategic air forces in Europe, filed a report that evening recommending immediate adoption of constant-speed propellers for all Army Air Corps fighters, bombers. He wrote, "This advantage is not an improvement, it is a revolution in the air. The performance advantage," he wrote, "is so significant that it represents a fundamental shift in combat capability." Any air force equipped with constant speed propellers will possess decisive superiority over opponents still relying on fixed-pitch systems. As 1934 came to a close, Hamilton Standard's production lines worked around the clock, the clang of metal echoing through the night. Orders from the Army, Navy, and civilian airlines poured in endlessly, a sign that a new era of flight had truly taken off. But across the Atlantic, darker events were unfolding, challenges that would test Caldwell's innovation under conditions no peacetime engineer could imagine. While Frank Caldwell continued refining his propeller designs in Connecticut, European aircraft manufacturers were falling dangerously behind American innovation. In the vast Messerschmitt factories outside Augsburg, Germany, the nation's most advanced fighter, the Bf-109, still relied on manually adjustable propellers, forcing pilots to constantly manipulate pitch levers during fine combat, while their American counterparts let engineering, not exhaustion, decide performance. The British Supermarine Spitfires and Hawker Hurricanes still relied on primitive two-position propellers, offering only coarse pitch for high-speed flight or fine pitch for climbing. No intermediate settings, no automatic adjustment. While German fighters could optimize performance at every altitude, British pilots had to fight their machines as much as their enemies, losing speed, fuel, and lives to mechanical limits. Across the burning European skies, those three self-adjusting blades, once dismissed as impossible, were about to prove they could change the balance of war forever. The deadly consequences of this technological gap became clear during the first months of the war. Royal Air Force combat reports from September 1939 painted a grim picture that kept Air Ministry officials awake at night. Above 15,000 feet, German Bf-109s consistently outclimbed British fighters, where manually adjusted propellers gave Luftwaffe pilots a crucial advantage. In those thin skies, the battle for altitude became the battle for survival. A few thousand feet meant the difference between life and death. Royal Air Force bomber crews reported aborting missions when their aircraft failed to reach enough altitude to clear the Alps or evade German interceptors. In the high skies of Europe, precious seconds were lost during climbs to intercept altitude, seconds that often meant the difference between victory and disaster. Many fighter pilots could only watch helplessly as German formations disappeared into the clouds, feeling the crushing weight of a war decided by mere seconds and a few hundred feet. Air Marshal Hugh Dowding, the methodical Scotsman commanding Fighter Command, carried a private fear that Britain's fighters were already outmatched in the coming struggle for air superiority. Intelligence reports from France described German pilots who could optimize their aircraft performance throughout every engagement, while RAF pilots wrestled with manual pitch controls, mechanisms that demanded constant attention at the very moment their focus should have been locked on enemy aircraft. In the thin air above Europe, every second spent adjusting levers could mean the difference between victory and survival, and Dowding knew that unless Britain closed the technological gap, the battle for the skies might be lost before it even began. At the 1938 Automotive Engineers Conference in Detroit, Caldwell presented data that should have alarmed every military aviation expert in attendance. His comparison of constant speed versus fixed-pitch propeller performance using identical engines revealed numbers that bordered on revolutionary. Static thrust, the power available for takeoff and initial climb, was 40% higher with automatic pitch control. The room fell silent. Caldwell wasn't just showing data, he was rewriting what power meant in aviation. Climb rate below 10,000 feet increased by 35%. Fuel consumption at cruise altitude dropped by 15%. Most significantly, the combat ceiling rose by more than 6,000 feet, granting properly equipped fighters a decisive advantage in altitude and reach. Yet, across Europe, aviation engineers dismissed these results, calling them nothing more than theoretical gains benefits that would, they insisted, turn deadly in real combat. What they didn't know was that these theoretical numbers were about to rewrite the balance of the skies. Dr. Ernst Heinkel, designer of Germany's fastest fighters and bombers, publicly argued that hydraulic propeller systems were nothing more than American over-engineering, trading reliability for marginal performance gains. British propeller manufacturers echoed his sentiment, insisting that manually controlled pitch gave pilots greater precision during the violent turns of air combat. What they failed to see was that in the skies of the new age, human precision could never rival mechanical intelligence. The production challenge facing Hamilton's Standard grew more daunting with every passing month as military orders multiplied beyond expectation. Each constant-speed propeller demanded 47 precision-machined components with tolerances measured in thousandths of an inch, assembled only by highly skilled craftsmen using specialized tools. Amid the hiss of metal and sparks of steel, human hands forged the mechanical heart of American air power, each propeller a masterpiece born from war. The East Hartford factory expanded to run 3 shifts, 7 days a week, its machines roaring without rest. Yet demand always outpaced capacity as the Army Air Corps, Navy, and Allied purchasing commissions competed for every available unit. In the chaos of wartime production, quality control became both Caldwell's obsession and his nightmare. A single batch of faulty governors, the critical components that regulated oil pressure and blade pitch, caused 3 propellers to lose hydraulic pressure during test flights at Wright Field. One small flaw, but enough to threaten the very trust in the system he had spent a lifetime perfecting. The failures occurred during simulated combat maneuvers, exactly the conditions where reliability mattered most. Army Air Corps procurement officers immediately threatened to cancel pending orders worth $12 million, a blow that could collapse Hamilton's Standard overnight. Critics across the aviation industry seized the moment, calling it proof that constant-speed propellers were far too complex for combat, where simplicity equals survival. Caldwell's response reflected the methodical determination that had defined his career. Working with Hamilton Standard's finest engineers, he redesigned the governor system in 6 weeks, adding redundant pressure circuits and backup mechanical controls to ensure that the propeller would keep operating even if the primary hydraulic system failed completely. Cold logic, steady hands, the mark of an engineer who never surrendered to failure. New testing protocols pushed every propeller to endure stress levels exceeding combat conditions by 50%. Most importantly, Caldwell established a personal policy: he would inspect and sign every single propeller before it was shipped to military units. It wasn't just engineering, it was a pledge of integrity, a promise from one engineer to every pilot whose life depended on his design. The improvements in reliability arrived at a critical moment. By early 1939, the Luftwaffe's strength had grown to over 4,000 aircraft, while the RAF Fighter Command possessed fewer than 700 operational fighters. The gap between them, if not bridged by Caldwell's innovation, might have changed the sky over Europe forever. German aircraft production was accelerating at a terrifying pace. New factories were rising across the Reich, producing advanced designs such as the Bf-109E model and the twin-engine Bf-110 destroyer. Intelligence reports confirmed that German bombers now possessed the range and ceiling to strike any target within Britain, while RAF fighters still struggled to reach those high-altitude formations. The technological gap became tragically clear during the Battle of France, as British pilots found themselves outclimbed, outgunned, and outclassed, a battle where science itself chose the victor. In 1940, over the skies of France, RAF, Hurricane, and Spitfire squadrons, still equipped with 2-position propellers, were fighting a losing battle. Above 20,000 feet, they were consistently outperformed by German fighters. Flight Lieutenant Douglas Bader, commanding No. 242 Squadron, reported bitterly, "German aircraft climb away from us at will above 15,000 feet. Our propellers simply cannot provide the power needed for sustained high-altitude combat." Those words were more than a report, they were the cry of an air force whose bravery outpaced its technology. Squadron losses mounted steadily, as RAF pilots realized that their aircraft's performance envelope was fatally inadequate against an enemy that could choose when and where to engage. By June 1940, with German armies advancing toward the Channel coast and the Luftwaffe preparing for its assault on Britain, Fighter Command faced a technological crisis, one that threatened the outcome of the entire war. The same constant-speed propellers that American test pilots had praised as revolutionary remained largely absent from RAF squadrons, victims of bureaucratic inertia and industrial fear of change. Squadron leader Desmond Cook of No. 65 Squadron at Hornchurch understood better than anyone what his pilots were about to face. Having flown Spitfires against German fighters over France, Cook knew that the RAF's performance deficits were not matters of pilot skill or aircraft design, they were engineering problems, waiting for engineering solutions. A battle of machinery awaiting a man who believed in mathematics over pride. As Luftwaffe formations massed across the Channel for Operation Eagle Attack Squadron, leader Desmond Cook knew the real battle was not only in the skies, but within Britain's slow-moving bureaucracy itself. Inside the operations room at RAF Hornchurch on June 10, 1940, Cook leaned over the table, the pale light from intelligence photographs glinting across his face. The images confirmed his worst fears: the German Air Force was ready, while Fighter Command was trapped in yesterday's technology. He realized there was only one chance left: act now, or watch Britain fall beneath the shadow of German wings. Across northern France, Luftwaffe formations were massing at forward airfields. Stukas, Heinkels, Dorniers, and the dreaded Messerschmitt escorts that had dominated the skies over France were gathering again, this time for Britain. Within weeks, perhaps only days, they would come across the Channel, and Fighter Command would have to meet them with aircraft that climbed too slowly and couldn't reach the altitudes where battles would be won or lost. In that moment, the fate of Britain hung upon the spin of a propeller. Cook had flown Spitfires over Dunkirk, watching helplessly as German fighters climbed away from his squadron at will above 20,000 feet. The mathematics were brutally simple. His aircraft took 11 minutes and 8 seconds to reach 20,000 feet, while Messerschmitt Bf-109s could reach the same altitude in under 9 minutes. In aerial combat, 2.5 minutes could mean the difference between life and death, and Cook knew that the one who rules the sky isn't always the bravest, but the one who climbs faster. In aerial combat, those 2.5 minutes meant the difference between intercepting enemy bombers before they reached their targets and arriving too late to prevent devastation. The solution already existed, hidden inside American factories, a breakthrough capable of saving Britain before the storm. But British bureaucracy moved with glacial slowness, while German invasion plans accelerated with each passing day. The clock was ticking, and the sky was running out of time. Out of time and patience, squadron leader Desmond Cook decided to bypass every official channel. He placed a direct call to de Havilland Propellers, the British licensee for Hamilton Standard's constant speed design. His message was clear and urgent: retrofit my squadron's Spitfires with American propellers immediately, with or without approval. The conversion program began within 48 hours, operating under emergency authorization from Air Marshal Hugh Dowding himself. De Havilland engineers worked around the clock, taking over every hangar at Hatfield to begin an emergency modification program. The once obsolete Spitfire Mark I aircraft, fitted with outdated two-position propellers, were now being transformed into fully automatic, constant-speed machines. Each conversion demanded 8 hours of precise craftsmanship, removing the old propeller hub, installing new hydraulic lines, calibrating the governor system, and performing ground tests to guarantee flawless operation. Under the warm factory lights, each Spitfire came back to life, as if all of Britain had placed its faith in every spinning blade. Fighter Command could spare each aircraft for only 24 hours, creating a logistical nightmare where squadrons operated with reduced strength while their planes underwent emergency conversions. On June 15, 1940, the first converted Spitfire rolled out of the Hatfield hangar. Squadron leader Desmond Cook personally conducted the initial test flight, taking off from the Grass Airfield in aircraft serial number K9847, marking the beginning of a new era for Britain's fighter force. The improvement was immediately visible during the takeoff roll. The propeller automatically shifted to fine pitch, allowing the Merlin engine to deliver maximum power while keeping its RPM perfectly balanced. Where his previous Spitfire had needed 320 yards to lift from the ground, the modified version rose smoothly after just 225 yards, a dramatic leap forward, proving that 3 spinning blades could change the course of a war. But the real revelation came during the climb test. Cook throttled to maximum continuous power and began his ascent toward 20,000 feet, the altitude where Fighter Command expected to meet German bomber formations. As the air thinned, the constant speed propeller continuously adjusted, maintaining steady engine RPM while automatically optimizing blade angle for maximum thrust. In that thin blue air, Cook realized this Spitfire didn't just climb. It felt alive, responding to every breath of the sky. At 5,000 feet, then 10,000, 15,000, the Spitfire climbed with a strength Cook had never felt in 3 years of flying the type. At 20,000 feet, just 7 minutes and 42 seconds, nearly 4 minutes faster than his previous best in an identical aircraft. Cook kept climbing, watching the altimeter tick past heights that once seemed impossible with the old propeller. 35,000 feet, 37,000. In that thin air, he realized a single innovation had unlocked an entirely new sky for Britain. At 39,000 feet, where the air was so thin that Cook's breath frosted inside the cockpit despite summer heat at ground level, the Spitfire finally reached its performance ceiling. The tactical implications were staggering. Fighter Command had built its defense plans around aircraft that struggled to reach 32,000 feet, requiring over 11 minutes to climb to intercept altitude. Now, in a matter of minutes, the Spitfire had shattered those limits, ushering in a new era of aerial supremacy. Suddenly, RAF fighters could fly 7,000 feet higher and reach combat altitude in 2/3 the time. German bomber formations cruising at 25,000 feet, once safe from interception, now faced Spitfires striking from above, armed with both altitude and energy advantage. When Cook landed at Hornchurch, he wasted no time grabbing the field telephone and calling Fighter Command. His message was short and urgent. The Spitfire is now a true weapon. The Spitfire is now an airplane. The message from Squadron Leader Desmond Cook echoed through Fighter Command headquarters, a single sentence that marked the turning point of an entire war. His next line was urgent and clear: request immediate conversion of the entire squadron. Within 72 hours, all 12 operational Spitfires of No. 65 Squadron had been retrofitted with constant speed propellers. The pilots' reactions ranged from astonishment to disbelief. They were discovering performance beyond anything they had ever imagined. Machines that climbed faster, responded sharper, and carried them higher than they had ever flown before. For the first time, they were no longer chasing the enemy, they were commanding the sky. Flight Lieutenant Brian Lane, a veteran of the French campaign, recorded the moment in his combat diary. "It feels as if someone replaced our engines with twice the power. We can climb with the 109s, now match them altitude for altitude. For the first time since this war began, we're not fighting at a disadvantage." Over the skies of Britain, Lane's words were more than a pilot's note. They were a declaration of triumph through engineering proof that 3 spinning blades had finally balanced the war in the air. Similar conversions began immediately across Fighter Command. De Havilland engineers worked 18-hour shifts, racing against time to retrofit Spitfires and Hurricanes before the German assault began. Across Fighter Command airfields, the numbers that would save Britain were no longer theory, they were becoming reality, forged in metal sweat and determination. By September 1940, 90% of RAF fighters were equipped with constant speed propellers, a silent revolution that transformed the balance of air power. Early Battle of Britain combat reports revealed a stunning leap in tactical capability. With the new propellers, RAF pilots could reach intercept altitude 2 to 3 minutes faster than German expectations. And with a service ceiling advantage of 4,000 feet, the Spitfires struck from above, the Messerschmitts attacking from heights where German pilots couldn't even respond. For the first time in the war, the Royal Air Force wasn't just defending Britain, they were owning the sky. Most significantly improved fuel efficiency, extended patrol endurance by 45 minutes, allowing RAF squadrons to maintain continuous patrols over German approach routes. The strategic impact reached far beyond the performance of any single aircraft. Air Chief Marshal Hugh Dowding's defensive system depended entirely on radar early warning and rapid scramble response to intercept German formations before they reached their targets. Those extra few minutes in the sky meant the difference between loss and survival, rewritten by Caldwell's constant speed propeller. Every minute saved in the climb to altitude multiplied the effectiveness of Fighter Command's limited strength. Pilots who had spent the summer of 1939 watching German aircraft climb out of reach now chose when and where to engage. The transformation was most visible not in speed or altitude, but in relief. The the reduction of pilot workload as constant speed propellers freed their minds for tactics and survival, not levers and engine strain. Constant speed propellers eliminated the need for manual pitch control in combat, freeing pilots from mechanical distraction. Now they could focus entirely on tactics and gunnery, not on engine management. Meanwhile, German pilots, still wrestling with hand-controlled propellers, fought their own machines as much as their enemies. When RAF Spitfires and Hurricanes appeared from above, they carried both altitude and energy superiority, advantages no British aircraft had ever possessed before. It was more than a technical upgrade, it was a revolution in air combat, where smart engineering gave human skill the freedom to prevail. As Luftwaffe formations massed across the Channel for the final assault on Britain, Fighter Command stood ready with aircraft that bore little resemblance to those that had struggled over France just months earlier. Frank Caldwell's impossible propeller had given the RAF the performance margin that would decide whether Britain survived or fell to German invasion. After Pearl Harbor, as America entered the war, Hamilton Standard transformed from a specialized manufacturer into the linchpin of Allied air supremacy. Every B-17 Flying Fortress, B-24 Liberator, P-51 Mustang, P-47 Thunderbolt, and P-38 Lightning required Caldwell's propellers to reach their full combat potential. The production demands were staggering beyond anything peacetime industry had ever imagined. By 1942, Hamilton Standard's order books listed 530,135 propeller assemblies, enough to equip every combat aircraft in the American arsenal and still provide spares for continuous operations across multiple theaters of war. A number that spoke not just of production, but of industrial power strong enough to change a war. In 1932, the East Hartford factory had only 800 workers, but by wartime, that number had expanded to 22,000, working 3 shifts around the clock. Manufacturing partnerships spread to Frigidaire, Nash Kelvinator, and Remington Rand, as automobile and appliance companies retooled their assembly lines for aircraft propeller production. At its peak, output reached 12,000 complete propeller assemblies per month, each requiring precision machining measured in thousandths of an inch, a technical feat unmatched in American industrial history. As mass production reached scales never seen before, quality control nightmares began to haunt Caldwell's nights and consume his every day. Failure rates increased as inexperienced workers struggled with complex assembly procedures that demanded precision measured in thousandths of an inch. Statistical analysis revealed a disturbing pattern, a hidden flaw spreading quietly through the very system built to power the war effort. Perfection, once Caldwell's pride, had become his curse. Every bolt, every propeller, every microscopic error now carried the weight of lives he would never meet. During the peak of wartime production, propellers built in haste began to show a troubling pattern, higher malfunction rates than those crafted in the careful pre-war era, when skilled craftsmen personally inspected every single component. The crisis reached its breaking point over the industrial city of Schweinfurt on October 14, 1943. The B-17 bomber, serial number 4231041, known to its crew as Hell's Angels, was fighting for altitude after flak bursts crippled its number 3 engine above the target. Amid smoke and shrapnel, that flying fortress battled not just the enemy but the consequences of rushed production. The feathering mechanism, designed to eliminate drag by rotating failed engine propellers parallel to the airstream, engaged normally during the bomb run, allowing the B-17 Hell's Angels to stay in formation. But during the climb to escape altitude, a manufacturing defect inside the hydraulic governor caused the feathered propeller to slowly turn back into the airstream, generating massive drag. The bomber was dragged nose down, spiraling into an uncontrollable dive over Bavaria. 9 airmen died when Hell's Angels crashed into the forest, a tragic reminder that one flaw in precision engineering could erase an entire crew. The subsequent investigation traced the failure to contaminated hydraulic fluid that had frozen solid at 30,000 feet, preventing the governor system from maintaining blade position. Quality control inspectors found similar contamination in 47 other propellers from the same production batch, all shipped to 8th Air Force squadrons operating from English bases. In the middle of war, a single flaw in inspection had become a tragedy written in steel and ice, and Caldwell now faced the coldest truth of his creation. At 33 minutes and 12 seconds, Frank Caldwell, now 54 years old, carried the weight of industrial responsibility no peacetime engineer could ever have imagined. He took personal accountability for the failure, no excuses, no blame. Caldwell flew to England aboard a War Department transport, visiting bomber bases across East Anglia to meet the air crews who trusted his propellers in battle. The conversations were brutally honest, filled with smoke, fatigue, and truth. But in those weary faces and oil-stained hands, he saw something no test report could show: the human faith behind his machines. Technical Sergeant Michael Romano, flight engineer on a B-24 crew, described propeller failures that had cost his squadron 3 aircraft in 2 weeks. "The feathering system works fine during training flights over Kansas," Romano said. "But over Germany, with flak fragments ripping through the sky and battle damage all around, these complex systems fail when we need them most." His voice carried no fear, only sorrow and disbelief for comrades lost, and for a technology once believed to be unbreakable. Back in Connecticut, Caldwell immediately began redesigning the feathering mechanism, the system that let a dead propeller turn parallel to the airflow. He added redundant hydraulic circuits and backup mechanical controls, ensuring that even if the primary system failed completely, the blades would hold their position. Amid sparks and steel, Caldwell turned failure into knowledge, turning mistakes into a stronger design than ever before. New quality control protocols subjected every propeller to environmental tests that mirrored real combat conditions. They endured temperature cycling from 60 degrees below zero to 140 degrees above vibration testing that pushed 75% beyond actual combat stress and contamination trials, where hydraulic fluid was deliberately polluted with metal particles, ice crystals, and chemical residues, simulating what could build up after long hours of warflight. It was more than testing. It was a promise of engineering faith. If a propeller was built to spin, it would survive the storm. By 1943, the reliability improvements had created the most dependable propeller system in aviation history. Combat loss statistics from the European theater revealed that propeller-related failures had fallen to less than 1% of all mechanical issues, lower than engine breakdowns, landing gear malfunctions, or electrical faults. What had once been a weakness, the feathering system now routinely saved aircraft and crews, bringing them home when engines failed under fire. The numbers proved more than engineering success. They proved that Frank Caldwell had turned the impossible into a legacy of survival in modern aerial warfare. According to 8th Air Force operational records, hundreds of bombers made it safely back to England after losing one or more engines over German territory. Their constant speed propellers automatically feathered, removing drag and allowing the aircraft to keep flying on the remaining engines. In the smoke-filled skies of Europe, every time those blades folded into the wind, instead of fighting it, a crew was saved, and another story of survival was written in the air. The strategic impact became undeniable as American aircraft met German and Japanese fighters in large-scale combat. P-51 Mustangs, fitted with Caldwell's constant speed propellers, showed decisive advantages over the Messerschmitt Bf-109. The K models delivered a 30-mile-per-hour speed edge and a 5,000-foot ceiling superiority, allowing U.S. pilots to choose when and where to engage. Across Europe and the Pacific, those numbers weren't statistics. They were the thin line between survival and loss. The B-17 Flying Fortresses could cruise 50 miles per hour faster than comparable German bombers, while operating 8,000 feet higher, placing them beyond the effective ceiling of most Luftwaffe interceptors. In the Pacific theater, the advantage became even more dramatic. The P-47 Thunderbolts, once dismissed as too heavy for dogfights, achieved 40% better climb rates than the Japanese Zero fighters when equipped with constant speed propellers. That margin wasn't just performance, it was the thin line between falling from the sky and coming home. The automatic pitch control allowed American pilots to maintain optimal engine performance during the rapid altitude changes that defined Pacific air combat. Meanwhile, Japanese pilots struggled with manual propeller controls, forcing them to constantly adjust the levers at the very moments when their focus should have stayed on the enemy ahead. This difference turned the constant speed propeller into an invisible weapon, giving American aviators the power to fight longer, aim steadier, and win faster in every aerial battle. General Carl Toohey Spaatz, commanding the United States Strategic Air Forces in Europe, summarized the transformation in a confidential report to the Pentagon. He wrote, "The constant speed propeller has given American aircraft decisive performance advantages in every theater where we operate." It was more than a report, it was a testament of an era, proving that an idea once deemed impossible had become the weapon that changed history. It was as strategically important as radar, long-range navigation, or any other single technology the Allies possessed. Statistical analysis conducted by the Army Air Forces in 1945 revealed that constant-speed propellers had directly prevented an estimated 15,000 Allied aircraft losses through improved climb performance that enabled escape from enemy fighters, higher service ceilings that allowed operations above interceptor altitudes, feathering capability that permitted safe return after engine failures, and better fuel efficiency that reduced forced landings due to fuel exhaustion. Frank Caldwell's impossible propeller, once dismissed as unworkable, had become the silent weapon that saved thousands of lives and helped win the war. Dismissed by experts as too complex for combat operations, Caldwell's invention had proven more reliable under battle conditions than any fixed-pitch propeller it replaced. The technology skeptics claimed would cost American lives had instead saved thousands of airmen while providing the performance margins that made Allied victory possible. 3 spinning aluminum blades, once called impossible, had become the heartbeat of freedom's sky.